Okay, welcome to all of you. In today's lecture, we will continue with the variational approach to optimal control system. Just to quick review, in the previous class, we have start our problem on the variational approach. It is applicable to optimal control system. We consider a plant x dot with condition initial point is given, final point is free. We consider our performance index as j equal to with terminal cost and integral cost, which is given here. With a mathematical consideration, we define our PI as V plus ds by dt, and plant is this. So, objective is to find out the optimal u, which will minimize the j and satisfy the plant. Our approach is the Lagrangian approach. So, first we define our Lagrangian L as V plus lambda prime G. G is, this is our condition which we have taken in the previous lecture. So, this whole define the V plus lambda prime and this is my G. So, this is my Lagrangian at the optimal point, define Lagrangian at the variation point, find out the increment delta j as j a u t minus j a u star t, which nothing but from this increment we find out the first variation delta j, which is given with this expression plus LTF delta TF. If the second term, which is del L by del x dot delta x dot, we expand by the integral by parts and we get the final equation as del L by del x minus d by dt del L by del x dot delta x t del L by del u delta u plus whatever is by terminal condition which is given. So, here the two variables delta x and delta u, we treat u to be the independent, x to be the dependent. We select lambda such that the coefficient of the delta x will be 0. So, this give me the EL equation as del L by del x dot minus d by dt del L by del x dot equal to 0. So, if this is 0, then independent variable coefficient of delta u will also be 0. So, del L by del u is 0 and my terminal condition is L of TF plus del L by del x dot delta x t at TF point, that equal to 0. So, up to this we have covered in the previous class. Now, the terminal condition is given with the delta TF, which is the variation at the TF point, and delta x of TF. So, if this is the delta x of TF, delta xf, so what I can write? I can approximate x dot of TF plus delta x dot of TF as delta xf minus delta x of TF, TF. What is this? Say delta x of TF is what? Value of the xt at optimal point plus delta x, which is the variation point. So, this value will have TF at delta TF point as this value. XF is the value at the TF point, and at TF point value of x star of TF del, that will be this value. So, difference between these two is my delta x of TF, and difference between the highest, the final value and value of xt at the TF point is delta xf. So, what we are saying, x dot of TF value of the optimal point plus what is the delta x dot of TF, that we are approximating as delta xf minus delta x of TF, and this because this is the value at TF point and this is the value of Tf plus delta Tf point, the difference between these two and divided by delta Tf, the difference between. So, this is we are saying nothing but my x dot of Tf plus delta x dot of Tf. So, this I can approximate with the value delta x of f minus delta x of Tf divided by delta Tf. So, with this value if I will cross multiply this, so I will get x dot of Tf multiplied with delta Tf, delta x dot of Tf, T multiplied with the delta Tf, these two value, and if I will take this the delta x of Tf. So, this equation I can write in this particular form, and from here I can find out the value of delta x of Tf. So, what actually we are doing with this expression, the final condition which we have taken as the L star at t equal to Tf point multiplied with delta Tf plus del L by del x prime multiplied with delta x t at t equal to Tf point, and I am saying my this condition is equal to 0. So, in this condition I will place delta x of Tf as delta xf Lt of Tf point delta Tf plus and delta x of Tf, which is this. So, I take delta L by del x prime and delta x of Tf, and this is also t equal to Tf point. So, this equal to 0. So, this delta x of Tf I am replacing with delta xf this is my delta xf minus x dot of Tf delta Tf, and this equal to 0. So, I can club this L delta Tf, this delta Tf term I can club together to get my final relation as L minus del L by, so this is nothing but L minus del L by del x, del L by del x multiplied with x dot t. This I will evaluate at t equal to Tf point plus del L by del x prime delta xf, and this I am evaluating at t equal to Tf and this equal to 0. So, my final condition will be can be represented by this equation, which is L minus del L by del x prime delta x dot, sorry, in this if I am taking this. So, this is nothing but x prime, and this is evaluated at Tf point. Similarly, del L by del x dot evaluated at the Tf point delta xf, this equal to 0 is my final condition. So, with this I have my Lagrangian equations as del L by del x dot minus d by dt. So, first condition I get as my EL equation, second is del L by del u 0 my control equation, this is my del L by del lambda equal to 0, this nothing but give me my del L by del lambda equal to 0, and this is my final boundary condition. So, these condition can be used to solve any optimal control problem in which u is not constrained. This can further be simplified if we will define a term called Hamiltonian. Hamiltonian is defined simply as my v plus lambda prime f, where v is the integrand of my performance index, while f is nothing but my state equation. So, what actually we have considered? So, from my j, which we have defined as the terminal cost plus integral of v dt, this was my pi and my system was x dot t equal to f dot, which is f x u t. In this I am defining my Hamiltonian simply as v plus lambda prime f, because x is the n number of the states. So, I have x 1 as x 1 dot t as f 1, x 2 dot t as f 2. So, in a way my Hamiltonian simply is defined as lambda prime we are writing as lambda 1, lambda 2, lambda n, f 1, f 2, f n. So, whatever is my system that I am taking as a condition, my condition in case of Lagrangian we have taken the x dot t minus f equal to 0, which I am representing as the g equal to 0. So, this was condition in case of the Lagrangian, but in defining the h we take this f along with the v represented in this way. So, Hamiltonian h can be written as a function of x u lambda t. So, we are defining our h as v plus lambda prime f, where h is a function of x u lambda n t. We already have defined our Lagrangian as v plus del s by del x, x dot t plus del s by del t, which is nothing but my integral inside the integral cos function plus lambda prime, and this representing my g. So, what we can do? We can define our L in terms of the h. So, in terms of Hamiltonian, if I will define my Lagrangian, which is nothing but h, which will include v plus lambda prime f, and what is rest left? Del s by del x x dot, del s by del t minus lambda prime x dot t. So, h defining is my v plus lambda prime f plus these three terms are left out from this, number 1, number 2, and the third is x dot multiplied with lambda prime. So, we can define my L in terms of H. Now, all the 4 equations which we have seen here, now these equations can be converted into the Hamiltonian form. So, that we will see how we can do this. Let us write it on the board. What actually is my L in terms of the H? See, what we are defining, L as my H, which is a function of x u lambda t plus my term with del s by del x prime x dot t plus del s by del t and minus lambda prime x dot of t. So, this is my L. Now, if we will see what is my first equation for ut, that was for optimal control. I have my equation as del L by del u equal to 0. So, my first equation is del L by del u equal to 0. If I will use L as H plus del s by del x x dot del s by del t minus lambda prime x dot t. If we will see, only H is a function of u. This is independent of u, this term is independent of u, this term is independent of u. So, this nothing but give me del H by del u. So, del L by del u I can write as del H by del u, which is nothing but equal to 0. So, if I will take del H by del u equal to 0, this will give me the control. So, solution of this will give me the u star t, whatever the value I will get. Then we have the EL equation, which is defined as this, we will left out as such. This was my del s by x dot of t, and this was my minus what actually we have, lambda prime x dot of t. So, this was my EL, and I have my EL equation as del L by del x minus d by dt of del L by del x dot, that is equal to 0. So, if I will take del L by del x, this is so del H by del x, if L I will use this plus del 2s by del x square x dot of t plus del 2s by del x del t prime minus d by dt del s by del x prime minus lambda star t, and this is equal to 0. See what we are doing, we are taking del L by del x. So, with respect to x I have to differentiate all this term. H is a function of x, so directly we will have del h by del x. Del s by del x is also a function of x. So, this is del 2s by del x square x dot of t, and x dot if you will say, so del 2s by del x del t. So, my first term will give me the first 3 terms, then d by dt of del L by del x dot, h is not a function of x dot, I have a function of x dot as del s by del x prime, and another function of x dot is lambda prime x. So, minus lambda prime equal to 0. So, this equation if I will further expand this part d by dt of this, what actually we will get? So, I have this term as such del h by del x plus del 2s by del x square prime x dot of t plus del 2s by del x del t minus d by dt of del s by del x, what actually we will get? Del 2s by del x square x dot of t plus del 2s by del x del t minus lambda dot of t, that all equal to 0. Now, if you will expand this, my this term will cancel out, this term will cancel out, and I will left only with del h by del x plus lambda dot of t equal to 0, and this will nothing but leads. So, if I will expand my this EL equation in terms of the Lagrangian, and Lagrangian I will use it in terms of the Hamiltonian. So, this equation finally leads to del h by del x equal to minus lambda dot t, and here this is known as my co-state equation. So, my first equation was the del L by del u equal to 0, which leads to del h by del u equal to 0. Second equation, the EL equation, del L by del x minus d by dt del L by del x dot equal to 0, this will leads to del h by del x equal to minus lambda dot t. So, in these 4 equation, these 2 we have seen, del L by del lambda is 0, from del L by del lambda my h is a function of lambda, and this x dot is also a function of lambda. So, now we are seeing the third equation del L by del lambda equal to 0, del L by del lambda equal to 0, this will leads to what? The first h is a function of lambda del h by del lambda, and last term minus x dot t, that is equal to 0. So, this simply give me del h by del lambda equal to x dot. and similarly we can place the value of the L in the terminal condition. So, del L by del lambda leads to this, and once we will place the H into my terminal condition, sorry, L in the terminal condition, I get H plus del S by del T delta T f del S by del x dot minus x dot T delta x f equal to 0. So, this will be my final condition. So, in terms of Hamiltonian, my equations are del H by del U equal to 0, del H by del lambda equal to x dot, which is called my state equation, del H by del x equal to minus lambda dot, called my co-state equation, and boundary condition as given by H plus del S by del T delta T f del S by del x minus lambda T delta x f that equal to 0. So, 4 equations in Lagrangian given here can be transformed in terms of the Hamiltonian as these 4 equations. So, our approach normally here is, for a given system we define the H, find del H by del U equating to 0, give me the optimal control. I take del H by del lambda, so I will have my state equation, del H by del x, I will have my co-state equation, and these equations can simultaneously be solved using the final boundary condition. So, what is the final boundary condition? As in this case we have assumed my boundary conditions to be initial point is fixed, but the end point is free. So, we have taken a journal case. So, we can have the different type of the system based on my terminal condition. These cases we can consider it as, number 1, we have the fixed final time and the fixed final state. So, these are the equations which can simultaneously be solved to find the optimal control for a given plant which is minimizing a given performance index. Based on the terminal condition, we have the different cases in which my final condition is changing according to the XTF and the TF condition. So, these cases we will take up in the next class. So, this class we ending here. Thank you very much.